Now, in this entire problem, you're going to set f of x equal to 0 and solve for x. Set f prime of x equal to 0 and solve for x. Set f double prime of x equal to 0 and solve for x. Each time that you're solving for x, what are you then going to do with x? Plug it right back into the original function and solve for y. Because your goal is always to find a coordinate in space. And the coordinate is xy. So we do all of this, f of x equals 0, f prime of x equals 0, f double prime of x equals 0. Every time you do that, what are you solving for right then? X. You're about to solve x. So then to find y, you always have to go back and plug it back into the original function. Okay, well then, let's go ahead and start off with, let's do this one blind. Like we won't look at the graph first, but can we all go ahead and guess what the graph looks like? Since it's still a parabola multiplied by an exponential function, do we all agree that it will probably go through 0, and then it will create a little speed bump to the left, and then create an asymptote? So we kind of already know ahead of time that's what it's going to look like. So now we're going to go find all those points. So let's start with, and I'll move my board up here in a second. Let's start with f of x equals 0. So that's our goal. So step number 1, I'll label it step number 1, f of x equals 0. So we go ahead and write down f of x equals x squared e to the 14x equals 0. And how do we solve for x? With a zero product rule. We have a product here. It's something times something equals 0. And so you can split that apart and say, well, either x squared equals 0 or e to the 14x equals 0. And on the left-hand side, you square root both sides and you get x equals 0. And on the right-hand side, you could do a couple of things. You could just write the word never. Never. And e to the 14x will never equal 0, because if you look at a graph of what e to the 14x looks like, it's that it blasts off to the right and goes up to infinity. And to the left, it's an asymptote, and it never reaches 0. It never reaches the x-axis. So e to the 14x will never actually equal 0 because it will never have an x-intercept. So there's no x-intercept. And so this equation will never be true. But the other thing you could do if you really wanted to would be to take a logarithm to solve for x. So you'd say log base e of 0 equals 14x. But as soon as you type log base e of 0 into your calculator, what does it do? Oh, try it. Do log base e, keep in mind, is really ln. It's really ln. On your calculator, log base e is ln. So what's ln of 0? Error. Right, so in any case, you cannot set error equal to 14x and then solve for x. So the whole thing is just never. Right, so that's two different ways you can think about it. Right? Okay, so then what does that mean? Our only x-intercept is at x equals 0, and that's already kind of what we knew over here. And do we already know this coordinate? Since it's at an x-intercept, we know the y value, so we can go ahead and label our first coordinate is 0, 0. And we'll just start that practice. Every time you solve for x, you immediately plug it back into the function and get the coordinate. Okay, let's do number 2. And number 2, we'll set f prime of x equal to 0. So first we have to find f prime of x. How do we calculate the derivative of a product? What do we do? What's the rule called? It's not just the power rule, the product rule. Yeah, the product, chain, and quotient are our 3 big rules. This would be the product rule, so it's the derivative of the first times the second plus derivative of the second times the first. There's our product rule. So the derivative of the first is 2x times the second, we just leave it alone, plus derivative of the second. And remember, how do you calculate e to the 14x? For sure, the derivative of e to the x is still e to the x. But we have an inside function. Inside of the exponent is 14x. So we have to do a chain rule. So the derivative of the outside is still e to the 14x. Keep the inside alone. Times the derivative of the inside function, which is just 14. So overall, the answer is 14 e to the 14x. It's kind of interesting to note this rule side by side with the power rule. So look, whenever you have the power rule, which is x to the n, so let me write that out real quick, f of x equals x to the n, so the derivative is nx to the n minus 1. Notice this rule. If you have f of x equals e to the nx, then what will the derivative be? N e to the nx. Look how similar that is. How is it the same? In both cases, you bring the exponent down. How is it different? Yeah, in this one, you leave the n the same. You don't subtract 1 from it. But in the power rule, you do subtract 1. So your brain could probably very easily memorize that these two things are very similar but different. So whether it's x to the n or e to the n x, in both cases, you bring the n out front. But only in the power rule, you subtract 1. Whereas e to the nx, you keep the nx the same. Okay, so the derivative of the second is just 14e to the x, hopefully, or 14e to the 14x, times the first, which is x squared. And then what's our clever algebraic manipulation that we do here? Yeah, we're going to pull out that e to the 14x up front, leaving behind 2x plus 14x squared. What? Oh, we could further take out an x. We could further take out a 2x. Sure. No, that's a fun idea. I wouldn't have done that, but I think that's a great idea. So now we can take out a 2x, leaving behind 1 plus 7x. Why is Nando's idea so fun? So remember, we're going to, after we find the derivative, we're going to set it equal to 0. Why is this idea so fun? Because now we have a triple product, zero product rule. So we're doing the zero product rule with 3 different things. And so here we say, when is e to the 14x equal to 0? Never. And when is 2x equal to 0? When x equals 0. And when is 1 plus 7x equal to 0? When 7x is equal to -1 or x is equal to -1/7. Okay, so what did we just find? We just found when the derivative was equal to 0, and derivative is synonymous with the word, well, yeah, flat spots or slope. Very good. And so these are where the slope was 0, which is a flat spot. So we have flat spots at 0 and -7. So going back to my graph here, I already knew that I had a flat spot at 0 because visually that was obvious. So a flat spot, but then I'm also going to have my flat spot here, which I now know is that the coordinate or the x value -1/7. But now let's go ahead and immediately plug that into our function and calculate the y value. So if I go ahead now and plug -7 into the original function, because we're looking for a coordinate, then what would we get? We would get f of -1/7 equals -1/7 squared e to the 14 times -1/7. Looks a little messy. -1/7 squared is 1/49. And then 14 divided by 7 is 2. That's e to the -2. I got 1/49th e to the -2, which we can further. What can I do with my e now since it's a negative exponent? I can push it down into the denominator with the 49. So it's really 1/49e squared. That's the y value. Of course, we just want a decimal, don't we? We would just want a decimal. That looks really nice. That's really nice and clean. But we would still want just a decimal. So you go 1 divided by parenthesis 49e squared parenthesis. And did anyone else get a decimal of 0.0028? It's really 0.00276. But we're going to round the 276 up to 28 because more likes 4 decimal places. So where's our coordinate then? This coordinate right here, you could either say is -1/7, comma 1/49e squared. But nobody would ever do that. You'd say -1/7, comma 0.002. I take it back. Somebody might do that. That's nice and clean. 149 squareds. How would you say that as a fraction? 1/49ths, but it's 149 squareds. All right, so that's a nice clean answer. That's, there's no approximation. You haven't rounded anything. That's a good clean answer. Whereas that would be a decimal. Okay.
The problem with having both a fraction
You mean like that's a fraction? Well, I mean, we could also write that as a fraction too, right? Because then 1/7 is just 0.142857. We could round that to 0.1429. So then what you'd have? Negative 0.1429. Yeah, then it would be completely a decimal, right? That's probably better. So this is the pure fractional answer, and that's the pure decimal answer.
Try to hit the fraction button on the other one. It doesn't.
Oh, like this decimal?
Yeah.
Oh, like if you then hit math frac?
Yeah.
It would not be able to do that because there's an E involved.
So it just doesn't.
It just wouldn't do it. Yeah, it would just return the same value. Yeah. All right, how does everyone feel about that so far? This is our process. We set f of x equal to 0, solved for it, plugged it back into the function to get a coordinate. Set f prime of x equal to 0, solved for all the values of x, and then plugged them back into the function to get the y coordinate. Any questions or feelings so far? All right, well, let's do the last part. The last part would be step 3. Let's find the second derivative and set that equal to 0. So first we have to find the second derivative. So what should we take the derivative of? This one or Nando's triple product? Yeah, probably this one, because the product rule is when you have 2 things being multiplied, not 3 things being multiplied. So we'll go back to this one, and we'll take the derivative of e to the 14th x times that polynomial right there. Now the product rule is still something times something plus something times something. And so the derivative of the first, derivative of the e to the 14x, hopefully now you all have memorized, it's just 14 e to the 14x, times the second, 2x plus 14x squared, plus the derivative of the second, which is what? 2 plus 28x? Is that correct? Yes. Yeah. Times the first, e to the 14x. And now the same algebraic technique, we can pull that e to the 14x out. Leaving behind, I realize there's a 14 here and this term. I'm just gonna write it down and distribute that in a second. I don't wanna do too much work all at once and make a mistake. So what I tend to do is just pull out the e to the 14x and feel very happy with that. And then I'll continue on and distribute my 14. I know some of you probably feel like you could have done all that immediately. And if you can do that immediately without making a mistake, then go for it. All right, so now we have that, and then we need to combine like terms, our 28x's. So e to the 14x, that's 196x squared plus 56x plus 2. And that's our second derivative. So, where did I get this 14? When I pulled out that e to the 14x, there was a 14 in front of it. So I left that 14 sitting in front of that parenthesis. Yeah. Sarah, thank you for asking that question. Another way to have seen that, Sarah, check this out. What if I had written it down like the chain rule suggested, which is e to the 14x times 14? Then it would have been a little more clear that there's a 14 there being multiplied by the parenthesis, and I'm just taking out the 14x. All right, good question. Okay, so now we've set that whole thing equal to 0. And by the 0 product rule, we either know that e to the 14x should be equal to 0, which it isn't, never. Or we have 196x squared plus 56x plus 2 equal to 0. Which, for kicks, I'll go ahead and take out a 2, because why not? I'll divide everything by 2, just to make all my numbers smaller. So now we have 98x squared plus 28x plus 1 equals 0. What are we solving for? Yeah, right now we're solving for inflection points, right? We found the second derivative, we're setting it equal to 0. This part won't equal 0, this part will equal 0. And by the time we're done, how many solutions will we have? 2. And those will be the inflection points. And now we have a quadratic, so how are we going to solve that? Can we factor it? No. I don't think it factors. We could certainly try to factor it, I just don't think it will factor. So instead we would do the quadratic formula. And so I'm going to move my space over to here to do my quadratic formula. I have A equals 98, and B equals 28, and C equals 1. And so x is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over to a, which is negative 28 plus or minus all that over 196. Now, if you were in a different class, solving the quadratic formula would be a big deal. And your teacher would say things like, show all your work and show every step. But for us, solving a quadratic is just one teeny little part of this overall whole process. So, you know, at this point, our goal is just to get these answers. So I'm just going to do that whole calculation under the square root of my calculator. I don't need to show a ton of work there. 28 squared minus 4 times 28. That gives me 392. And then at this point, can you square root 392 cleanly? Does anyone know off the top of their head is 392 a square number? It is not. So all I'm going to do now is rewrite this as negative 28 plus or minus a decimal. Now, again, the Moore system wants 4 decimals of accuracy. So how many decimals of accuracy do I need to keep right here? More than 4. Because we're about to add that to another number and then divide by 196. And dividing by 196 will theoretically change some of those first 4 decimals of accuracy. So if you only keep 4 decimals of accuracy before you get to the very end, your answer won't be as clean. And in fact, just to prove it to all of you, we could even try. Let's see what happens if you just did negative 28 plus or minus 19.7989, which anyone would have rounded that to 90. So really, if you had rounded already, you get this answer. And so let's see what those 2 answers are. We have negative 28. I'll do both. You can just do the long one. Just do the long one on your paper, but I'll do this one up here to show that it gets off a little bit. So those are my 2 answers if I round before I get to the end. 7, 9. These are my 2 answers, negative 0.24. Oh, darn it. But it's not even going to make a difference. All my principled stances mean nothing. Oh man, it made no difference at all. All right, well, you have to watch out for that, though, because it could have made a difference. Do you believe it could have made a difference? Rounding too early in your calculation could make a difference and then throw it off. In this case, it didn't matter. All right, so that's what our 2 different values of x are, and we're done. So that's our values of x. Now I can go back to my graph. I can still see all that. So now my 1/7, let's just remember that's negative 0.1429. So now I have a value at negative 0.24, which is over this way a bit, negative 0.2439. So there's my inflection point. And then I also have one at negative 0.04, which is more over here. 0.0418. And there's my other inflection point. Okay, now what do we still have to find? We found all of our x's, but what do I have to do with these 2 x's now? Yeah, we need to plug those back into the original function to actually get the y value. So let's do that. Now, plugging those decimals into the original function, should we have more than 4 decimals of accuracy before we plug it into the function? Yes. See, that's the thing. You never want to round answers and then use rounded answers in any computation. So in theory, what I should have done here is actually typed out all the decimals of accuracy. So the 2 numbers I'm actually going to plug into my function now are f of negative 0.04, 184, 1888. And again, will it make a difference? I don't know, but I want to try to be careful. And then my other one would have been f of negative 0.2438, 7239. And I'll plug those values into my function.
You might say, Mr. G, you're kind of being crazy about all these decimals of accuracy. And maybe, because nobody's life is on the line right now. But if somebody's life was on the line, I hope that you would use as many decimals of accuracy.
Not necessarily.
All right, so now we have to type all that into x squared e to the 14x. So we're going to do that squared times e to the that times 14. My answer for this one was 0.00195, which is actually 0.0020. So for this one, my coordinate is now negative 0.2439, 0.0020. And then I still have to solve this one. So that would be negative 0.01. Squared times e to the 14 times that. And hey, what do you know? That answer came out in scientific notation. So then now the 0.000975, which rounds to 0.000, actually 0.0010. The 7 rounds the 9 up to a 10. So I got 0.0010. Okay, so then there's that other coordinate over there. So that'd be negative 0.0418, comma 0.0010. Okay, and there, what we see up here, which I wish I had drawn this bigger, but I hope you can all see that. That would be your final answer, but maybe a little bigger so that it's not so ugly looking. You know, it's not ugly, but it's really crammed in there, isn't it? It would look better if I had a really nice big graph to show.
Could I make it look good?
Yeah.
If I actually made it nice, big, and even exaggerated it a little bit to get the points far away from each other. And furthermore, since I know that this one is at 0.002 and this one's at 0.001, I know that this inflection point should be taller than that inflection point, right? So now, what would my really good graph look like? I would have negative 0.1429, 0.0028. And then this inflection point was at negative 0.2439, 0.002. And then this one was at negative 0.0418, 0.001. And then this one was at 0, 0. Okay, is that everything? Does that look like a good answer?
More or less.
Thanks, Josh. More or less. What's the less part? My handwriting? That's fine. I understand. Yeah, more or less, that looks good. So, but what we could do now is go in there and actually label a few things. So we know that like that has slope of 0, and you could call that a flat spot. And then you could go right here, and you could call this an inflection point. You could call that an inflection point. And then you could call this another flat spot. And you could call it an x-intercept. Okay. Now, Josh, how about that? Does that pass your inspection? Is that better? Okay. Yeah, the more details, the better, right? We spent a little time on this problem because I wanted you to know what a good professional answer looks like. You know, other than my handwriting. Not it?
So initially we already knew the shape. So say you wanted to graph it, but you didn't know the shape.
You actually didn't.
Yeah.
Yeah.
So how would you go about doing that? After getting all your zeros.
Yeah, okay, well that's a great question. So let's imagine what we'd have if we didn't actually know what the shape was. We would just have a flat spot, an inflection point, and an inflection point. Is that fair? That's what we have. And that's what Nanda's asking about. So what do we do now?
Look at the
No, Nanda, is it fair to assume that we know that that's a max and that's a min, or are we not assuming that?
yeah. Assume that.
Okay, because we can find that real easily, right? By plugging that into the second derivative. By plugging that value and that value into the second derivative, if it was a positive number, it'd be concave up, and if it was a negative number, it'd be concave down. So, okay, so let's just say that this is all we knew, folks. Which is really interesting, because to be fair, what did Newton know? That.
right? So that's all he knew as well. So then what would we do? Do what? Yeah, you connect the dots. One thing you could do now to make this even better is a table of values. Because if you now knew, let's say this point was over here at what, negative 0.24, and what you could now do is a table of values, and you could just go ahead and do some table of values, say, what do you think? Probably every 0.01. So if you were really excited about this problem, you could do a table of values every 0.01, and you would do negative 0.01, negative 0.02, negative 0.03, negative 0.04. This would take up most of your afternoon. You plug all those values in, and then you would have that, right? So you do a table of values, you get lots of dots, and then you could genuinely, as Josh said, connect the dots.
So if you plug in your inflection points into your second derivative and you find the concavity, would you just get that maximum there anyway? You get what I'm saying?
Say that again, because if you plug inflection points into the second derivative, it'd be zero.
Like an inflection, a point to the left or the right.
Oh, yeah. If you plug a point to the left into the second derivative, it'd be positive. Yep. And then if you plug a point to the right of the inflection point, it'd be negative. Then if you plug a point still to the left of that inflection point, it'd be negative still. And then a point to the right of that inflection point, it'd be positive. Yeah, and then that way you would know that like this whole chunk should be concave downish, and this whole chunk should be concave upish, and that chunk should be concave upish. Yep. Okay. How does everyone feel about this? I'd say that was a fairly long, extended example. Now I wonder, did we even read the problem? No, let's read it. So consider the function, consider it. Have we considered it? We've considered it thoroughly. Okay, so for this function, there are important intervals from negative infinity to a to b, and b to infinity, where a and b are critical numbers. What are critical numbers again? Yeah, critical numbers are the flat spots. So what they're saying then is that a and b are what values? A and b are these numbers right here. But we need to make sure we put them in the right order. A and b, so I've got 0 and I've got negative a seventh. A is this one, b is that one. We all agree? Not in this problem. They're saying a and b are critical numbers. Yeah, the other problem said inflection points. This problem says critical points. So everyone draw a little number line with me here. We've got a little number line. They're saying that a and b are important numbers, and they would like to know, for each of the following intervals, tell whether it's increasing or decreasing. So this is a completely separate problem than what we did before. So is the function increasing or decreasing? So over here to the left of negative a seventh, is it increasing or decreasing? To the left of negative a seventh, it's increasing. Right? And then what about between negative a seventh and 0? Between negative a seventh and 0, it's decreasing. And then what about to the right of 0? It's increasing. So the answer that they're actually looking for here, if I can, oh, yeah, I can do that. What they would have wanted you to do to write down or to type in is that from negative infinity to negative a seventh, that graph is increasing. And from a to b, that is from negative a seventh to 0, the graph is decreasing. And then from b to infinity, that is from 0 to infinity, the graph is increasing. And that's all they were actually wondering about in this problem. Yeah, we did a lot more work to fully understand the problem in a different way. But now, let me show you how to answer the problem that they were asking without looking at the graph. Kind of like Nando's question, what if you didn't have a graph to look at? So first of all, we did find the critical numbers, 0 and negative a seventh. And I want you to watch here what we're going to do. We have our number line here, and we want to know what is the graph doing here, here, and here. To the left of negative a seventh, in between negative a seventh, 0, and to the right of 0. Well, what you would do is, first of all, if a graph is increasing, what can you say about its slope? Positive. And if a graph is decreasing, the slope is negative. So here's what we're going to do. You're going to choose test values. So I would write that down. Choose test values. And I would choose the easiest test values you can come up with. So choose a test value to the left of negative a seventh. What's a number to the left of negative 0.14? It's really easy. Negative 1. So I would choose the number negative 1. Now choose a number between negative a seventh and 0. Remember, that's negative 0.14. So choose a really easy number between negative 0.14 and 0. That would be further left. Yeah, 0.1 would be a good one. So now negative 0.1. now choose a really easy number to the right of 0, 1. So these are our test values. We're going to plug test values into what? If you plug it into the original function, that's just going to tell you a y coordinate. You plug it into the derivative. So plug test values into f prime of x. Because f prime of x is a slope, and that's going to tell you if the slope is positive, it's increasing. If it's negative, it's decreasing. So now, you might be thinking to yourself, oh man, I'm already tired. I don't necessarily want to plug -1 into f prime of x and -0.1 into f prime of x and 1 into f prime. This might look like, oh man, this is more work on my calculator. But look how simple it actually is. The function is x squared e to the 14x. Right? Oh, no, I'm sorry, the derivative. I just wrote down the original function. The derivative, where's the derivative? Is it e to the 14x times 2x plus 14x squared? Okay, so, boy, I should write it down once. Plug test values into f prime of x. So here's f prime of x, which is e to the 14x, and then we have 2x plus 14x squared. Okay, so I'm going to plug each of these numbers in, and if the number is positive, that means the slope is positive, so it's increasing. And if the result is negative, that means the slope is negative and it's decreasing. So first of all, no matter what I plug in to e to the 14x, will that be positive or negative? It'll always be positive. So I don't even have to plug the number into that, because I already know that no matter what I plug in e to the 14x, that's positive. So now I just need to know what happens if I plug my numbers into this. And fortunately, because we chose such easy numbers, we can do this in our head. So 2 times -1 is -2, plus 14 times -1 squared is 1, times 14 is 14. And so my first value, 14 minus 2, is a positive times 12. That result is positive, and therefore the first chunk is increasing. Is that what we said, that the first chunk was increasing? Yeah, the first chunk was increasing. Okay, so now what if we plug in -0.1? If I put a -0.1 in for x, 2 times -0.1 is -0.2. And then I would actually have to do this on my calculator. So -0.1 squared is 0.01 times 14. Oh, it's actually 0.14. And so what's -20 cents plus 14 cents? That's negative cents. And then positive times a negative is negative. So that tells us that that next chunk is decreasing because it has a negative slope. And then the last one, if I plug 1 into all that, again, we can just do this in our head very quickly. 2 times 1 is 2. 1 squared is 1 times 14 is 14. So that's 2 plus 14. That's also a positive number times a positive number, and therefore the result is positive, and therefore that part of the graph is increasing. So what I just demonstrated for you right there is a process called test values. Choosing test values and plugging them into the derivative to just see real quick if it's increasing or decreasing. Notice this was really off the cuff. Did that feel very unprofessional? Like I was just like, well, that part's positive. Don't even need to know what it is. And then like here, it's pretty easy to see whether the result was going to be positive or negative. I didn't even bother doing the calculation. I just noted if it was positive or negative. Okay. We did a lot in that problem. And we will do more problems like this. Because right now you might be saying to yourself, golly, Mr. G, what do you want me to do? That whole long, big process? Or just the test values process? Or draw the picture? And I mean, ultimately, I'd like to do all of it. But no, the instructions will be very clear. Yeah, the instructions will be clear as to what I want you to do. So for now, let's all take a deep, deep breath. We're going to move on from this problem, try another problem. I won't make us do so much going forward. But that was a really good problem. And I'm really glad that you got to see the whole process. Every single step. And again, you can go online. I emailed you all of this process on a piece of paper. And I do intend to give you just one problem like this on the test. And it would take up a full page to go through that whole process and find all those points. Thoughts, feelings, questions? Or keep going? Good questions, was it? What did you say, Rosa? Is that a lot to do during the test? What if that was the only question? No, I'm kidding. It won't be the only question, but I will make sure that you have enough time to do it all. All right, well. The name of this section, 2.8, was called curve sketching. Did we sketch a curve? Yeah, and did it match what's on Desmos?
Can you check?
Yeah, we can check. That's probably a good idea to check. So let's check. Now remember, checking your work online, as much as I'm sure we're all excited, like, yeah, let's go online and check it. You know, you still have to zoom in the correct amount. Right? Because right here, that doesn't look like anything. You see it? Yeah. So no, I do not see what we just sketched. And even if I zoom right now, still don't see it. Zoom, still don't see it. Oh, do you see a little bit? Do you just barely see that it's rising up right there, that little speed bump? So what would I then need to do? I would need to change my window and change my y values to be like negative 0.05 up to 0.05. That exaggerates it a little bit. I'm going to actually go 0.005 and 0.005. Oh, there we go. There, that looks really nice. And that's what all we just found. There's our maximum at negative 1/7, just like we thought, at 0.0027. Our minimum, and again, inflection points are not on here. But I could draw the inflection point at, was it negative 0.24? Do you agree that it's concave upish to the left? And concave downish to the right? And then where was my other x equals negative 0.04? There we go. Is it concave downish in the middle? And concave upish to the right? Yeah, so everything's looking good. All right. If you feel a little tired right now, that's okay. That is okay. Okay, number 3. Again, you all know how to do this one. Let's just skip it. You can cross the whole thing out. That's fine. Yeah, you can just cross it out. I don't know why there were so many. Number 4, you can cross out too. I mean, unless you want to go back and do it, you certainly can. But I feel like we've already discussed these. Okay. You can actually cross out 5 and 6. I meant to delete those and I didn't.
We don't want to do the anti-derivative.
What?
We don't want to do the anti-derivative.
Well, we'll do that in chapter 3. Yeah, we'll do plenty of antiderivative. All right. Oh my gosh. Oh, good. Okay, yeah, there are some trickier problems. Okay, so here we are, number 7. What do we need to know? It says below is the function, over which intervals is the slope. What? How would you read this? See, there's a difference between reading it in math and then reading it to a friend. So in math, you'd say f prime is greater than 0. But how would you say it to a friend? What are you looking for? You're looking for a slope that is greater than 0. You like your friend even more. You're looking for a positive slope. Yeah, there you go. If you really like your friend, you would say, over which interval is there a positive slope? Versus, you know, if it was an enemy, you'd say f prime is greater than 0. Okay, so where is the slope positive?
To the right of the x.
Yeah, there you go. So that's it. The slope is positive to the right of negative 4. And so the interval would be negative 4 to infinity. So again, to an enemy, you would say f prime is less than 0. But to a friend, you'd say, yeah, slope is less than 0 or negative slope. And so the slope is negative from where to where? Now, it has this third question. Over the interval, the whole interval, from negative infinity to infinity, this function is? Yeah, I think they're looking for concavity. That was not at all obvious, was it? You could have said this function is a parabola. This function is smiling. You could have said a lot of things, but I think that they meant concave up. Yeah. Yeah, I think concave up is the right answer, especially if you look at the answer key. That's probably what they wanted. This function is fantastic. Okay, same thing for this one. Let's leave that be and move on. So number 9. Oh, number 9 is nice. So now this question isn't talking about slope. This question is talking about concave up. Now you notice they gave it to us as a friend. How could they have written it in math? Right? That's what it would have said. And likewise, concave down, that's friendly. If they had written it in math, it would have been like that. So taking a look, where do you all think the inflection point is? Does it appear to be at -1?
Yes.
Is that fair? To the left, is it concave upish? And to the right, is it concave downish? Yeah, so probably the inflection point is at -1. So the inflection point is at -1. To be really fair, they're saying there is an inflection point at, and they didn't say x, they just said where is the inflection point? So where is the inflection point?
-1.
Yeah, -1, 2. That's, that's not clear what they wanted. Did they want an x value? Did they want a coordinate? Who knows? But give both answers. Okay, and likewise, you can all write down the intervals. It's concave up from what, -infinity to -1? And it's concave down from -1 to infinity? Is that all fair? See, sometimes we do a problem like number 2 where it like takes 20 minutes and we're exhausted afterwards. And other times they just want to make sure we all understand the vocabulary and how to talk. Okay, now I know my phone already went off. I'm just trying to get through all these simple ones before we get to another one like this with a star next to it. That means that we're going to have some fun. So let's finish number 10 and 11, and then we'll take a break. So number 10, we've talked about this one before. Out of those 3 graphs, which one is the original function, which one is the first derivative, and which one is the second derivative? And don't shout it out just yet, but think about how you know. What do we know about a function, its derivative, and its second derivative? And generally speaking, what happens to the shape of those functions as you continually take derivatives more and more? So if your original function is a polynomial and it's very wiggly, what happens to the wiggliness as we move down? It smooths it out, becomes less wiggly, becomes straighter. And in fact, you can even prove that if it's polynomial, the number of turning points, so look at the turning points, it turns, 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 we call those turning points. The number of turning points decreases by 1 every time you take a derivative. So which one of those functions is the original? The green one. And how many turning points does it have? 2. So now we know that the original is green, it had 2 turning points. And now which one is the first derivative? Yeah, the red one. And how many turning points does it have? Just 1. And then the second derivative would be blue. And how many turning points does the blue one have? None. So the number of turning points goes from 2 turning points to 1 turning point to no turning points. I think I mentioned that in the textbook. Again, that's only if it's a a polynomial. Because we don't study trig functions in here, but you know the trig function, the sine of x? Well, the sine of x has a graph like this. And that has infinitely many turning points. And when you take the derivative of sine of x, you actually get cosine of x. And that still has infinitely many turning points. So the turning point thing only applies to polynomials, not functions in general. Okay, last question. We have number 11. It says, let f of x equal 3 minus 3x cubed. And it says f of x has 1 critical value. And then they want to know, for whatever that critical value is, look to the left of it. Is the function increasing or decreasing? Look to the right of it. Is it increasing or decreasing? So everyone take your function, write it down in your own hand. And what are they asking us to do? It says f of x has 1 critical value at a. So what's a critical value again? It's not f of x equals 0. Which one of these is a critical value? Just this one. This one's called a critical value. This one's called an inflection point. And this one, the first one, is called a solution or an x-intercept. So that's the way they'll use words. A critical value always applies to the first derivative set equal to 0. And inflection point always means the second derivative set equal to 0. And a solution or x-intercept is f of x equal to 0. So what are they asking us to do? Yeah, find the derivative and set it equal to 0. So you can memorize that that's what critical value means. It means take the derivative, set it equal to 0. Okay, so how are we going to take the derivative? What rule applies? Yeah, it looks like the chain rule. Why is it the chain rule?
There's an inside function, 3 minus 3x, and an outside function, something cubed. So to do the chain rule, we do the derivative of the outside. Would it be helpful if I had colors here? Derivative of the outside, so that would just be 3 something squared. Leave the inside alone. And then multiply by the derivative of the inside. And what is the derivative of 3 minus 3x? Negative 3. The derivative of 3 is nothing. The derivative of negative 3x is negative 3. So now our derivative, we can multiply those coefficients together. So that gives us negative 9 and then 3 minus 3x squared. So that's our first derivative.
So you don't do 3 times 3.
Yeah, I just did 3 times 3 and I put it out front as the 9. What are you talking about? Oh, like distributing?
Yeah.
Ah, can I distribute when this thing is being raised to a power? No. Because think about what it actually looks like, Rosa. It's actually 3 times 3 minus 3x times 3 minus 3x. So even if you did want to distribute it, it would only distribute it to one copy of it, not the second copy. Does that make sense? Okay, good. Okay, so now we set it equal to 0. And this algebra is pretty straightforward. We divide off the negative 9. That goes away. We square root both sides. That goes away. We subtract off the 3. Negative 3x equals negative 3. And we divide off the negative 3. And x equals 1. Did anyone else get x equals 1? That was a whole lot of algebra I just did for a result we probably could have all guessed. How could I make 9 times 3 minus 3x squared equal to 0? By the zero product rule, what must this inside parenthesis be? And how can I make 3 minus 3x be equal to 0? If x is 1. Yeah, so we could have guessed that answer. Okay, so now we know that our value of a is 1. And so again, I'm going to demonstrate this test value procedure. If I make a number line and I put a equals 1 in the middle, let's choose an easy number to the left and an easy number to the right. So what's an easy number left of 1? Try 0. What's an easy number to the right of 1? Try 2. And they want to know if it's increasing or decreasing. So what function we plug it into? F prime, or f double prime? I want to know if it's increasing or decreasing. I want to know if it's increasing or if it's decreasing. Which one should we plug it into? F prime. Because f prime tells you slope, and that tells you it's increasing or decreasing. So I'm going to find f prime of 0 over here, and I'm going to find f prime of 2 over here. And I don't even have to evaluate it completely. I just need to know what the sign is, positive or negative. So again, you could probably do this in your head. If I plug 0 in for x, I'm going to write the function. F prime of x is negative 9, 3 minus 3 x squared. Yeah. So if I plug in, do they really want to do this? It has one critical value, and the critical value is the flat spot, right? Yeah. Okay, well, this is really fun. I hate to get too far ahead of myself because I don't want to be wrong, but what happens anytime you square a number? Is it positive or negative? Positive. Positive, and so this thing is always going to be positive. And then a positive times a negative is negative. So this thing is always going to be negative. It's just always going to be negative. Well, let's do the math anyway. If we plug 0 in, 3 times 0 is 0, 3 minus 0 is 3, 3 squared is 9, 9 times negative 9 is negative 81. Now plug in 2. 3 times 2 is 6, 3 minus 6 is negative 3, but negative 3 squared is 9, and 9 times negative 9 is negative 81. So in both cases, what's happening to the right of A and to the left of A? It's decreasing both ways. What? No, you don't need a large number. It's just absolutely, this graph is always, if you go to x equals 1, it's always decreasing. Oh. Yeah, because it is a cubic after all. So a cubic can either look like that, always increasing, or the cubic could look like this, always decreasing. So it turns out that what we're looking at is just a cubic that's always decreasing.
Okay, so again, that was an example of a test value method. Where, did we ever graph this graph at all? No. And yet, theoretically, from the derivative alone, we were able to find out that to the left of 1, the slope is negative. To the right of 1, the slope is negative. And what about at 1 exactly? What's the slope? Yeah, because that was the value we found when setting the slope equal to 0. So, that's it. Let's take a break. When we come back, we can do some more exciting problems and some more exciting examples of test values. So let's see, the time is 12:02. I'll be back at 12:12.
You taking a lot of emergency?
Yeah. Just whenever I think about it, I actually take some. Because I've got toddlers at home and they kind of are sick right now, so I figured why not boost my immune response.
It's crazy when you read it. Are they taking 1,000% vitamins?
Oh, I know. I'm a big believer in mega doses. Like I'll easily take 3,000. Like I just took 3,000 right now. But that's
3 of them?
what?
3 of them?
Yeah. Yeah, and I would easily do 3 more tonight before I go to bed. Why is that? What? Oh, I know. I don't understand. That's been sitting here for so long.
I might take it at the end of the year.
Henry, I think you can take it now.
What is it?
I have no idea. Well, it's for weightlifting. All right, folks, let's keep going. So let's see, 13, 14, 15, 16. So we have 4 more problems. Let's just kind of look at them at a glance, shall we, to see what we're trying to do. There are 4 functions. I want to show them each to you. I'm going to reset Desmos. Hey, have you folks gone home and used Desmos yet?
Yes.
Okay, I mean, it's a really great website. I hope that you all just go home and play around with it a little bit. You know, at the very least, play with it while you're watching your Netflix or something like that.
I
You can
just
always-
get confused like moving around the X and the Y.
It is a little confusing. It takes a while to get used to it, for sure. Like, as an example, this function. So, you see, I just typed it in, and I'm looking at that, and I'm like, well, okay, it looks awfully skinny. So what would I do right now to make it look better?
Move the Y.
I want to get rid of all the x-axis to the left and get rid of the x-axis to the right. So I go up to my wrench, and I'm going to make my x-axis only go to the left. What? I mean, the red line stops at around -5. So I'll only go to the left, -6. Then how far to the right should I go? I mean, the red line only appears to be to the right about 2. So maybe I'll go 3. So now already this is better, but I'm missing the top half of my graph, so I need to go up considerably. So I'll make my y-axis go up to maybe 100, maybe 200. Whoop, I had to go up a lot. But now that I've gone up a lot to capture that, I can't see the detail down here anymore. So it's really a problem, because sometimes in order to get the detail that I want up there, I have to lose some of the detail down here. And it looks like I can't do both. So in this particular case, I know I have a maximum way up there, but I'm a lot more interested in what's happening right here. There are 4 gray points. I wonder what those are. So I'm going to have to go back to change my y-axis again and only go down maybe 100 and up 100. And so now I can see all that. This is much better, because now I can see this detail. And what's up here?
Well, we don't tell them.
Yeah, this is one maximum, you know, so I can keep that in mind. So there we go. That's our first graph. And now what are they asking us? It says f of x has inflection points at D, E, and F. So how do I solve inflection points? Yeah, I need to do the second derivative equal to 0. Now will give me all my inflection points. And then notice, once I find those inflection points, it wants me to create a number line and then find the concavity in between each of those inflection points. So that's what we're going to do here, is I'm going to take this polynomial, take the second derivative, set it equals 0, find my inflection points, create a number line, choose some test values, and then figure out if it's concave up or down. Before we actually do it, let's look at the next one. No, maybe that's going to be, we'll just do one at a time. I just want you to see that generally speaking, do all these problems look structured the same?
Yes.
Yeah, they're all looking for intervals. And in those intervals, we're just going to say, is a concave out, concave down, or what. Okay. So we know what our graph looks like. Let's do it.
You can go ahead and get started. You know that you're going to take your function, find the second derivative, and then set it equal to 0. So away you go. Take the second derivative, set it equal to 0, solve for x. So my function. So our first derivative, did anyone get 60 x to the 5th plus 180 x cubed minus 240 x squared? Hmm? 60 x to the 5th. 180 x cubed. Oh, yeah, thank you. Thank you, Colleen. Thank you, Rosa. It would be. Oh, I wrote 6. Boy, the brain can do some surprising things. 4. Okay, so that's our first derivative. And then our second derivative. Did anyone else get 240x cubed plus 540x squared minus 40x? Sure. Oh, except that's our second derivative. There we go. And so now that we set equal to 0. So what can we do? This is not the quadratic formula. It's a cubic. What can we do? We can take out an x and give us 4. 4? Well, we can take out 40 at least. What goes into 240, 540, and 480? I think 60, because in the previous row, 60 goes into all of those. So 60 must still go into all of those. So let's start with 60. Let's see if taking out 60 does the trick. So that'd be 4x squared plus 9x, sorry, x cubed. I have a problem. X squared minus 6 goes to 80. No, just 8. Okay. And yeah, now we can see nothing else can come out of 4, 9, and 8. I'm really having a problem. That's x squared. That's x. Oh no. All right. Now is that correct? 4x squared plus 9x minus 8? Is that what everyone else has? All right. So now what does this mean? We want to solve for 0. We want to solve for x. So on the one hand, we can use the zero product rule right now. And we can say that when this is 0, which is when x is 0. And then when this is 0. Now how do we solve that? Yeah, we just do the quadratic formula. Unless it's factorable. Does anyone think that's factorable? I don't think it is factorable. So a quadratic formula it is. We'll do x equals negative b minus square root b squared minus 4 times a times c. Did anyone get 209 under the square root? Negative 9 plus or minus root 209 over 8? Yeah. Okay, so now that gives us 2 different decimals. So on my calculator, just so you'll see it, I do parenthesis, negative 9 plus root 209, and then another parenthesis, divide by 8. And then after I get that result, I can hit second enter, pull that same thing up again, and just change my plus to a minus. That allows me to get my 2 decimals pretty quick. Now, how many decimals am I going to write down? All of them.
All right.
I'm gonna try to go with this,
Yeah, and I think what's happening here is that divided by 8, they think that you're only dividing that square root by 8. You'd still need a parenthesis there. Now, as you see, that was a bigger parenthesis that wrapped the whole thing up and divided by 8. Okay, so did we do it? Those are our inflection points. And they're saying that we want to read from left to right, from DE to F. So what I would recommend you do is make a number line and say my inflection points were 0 in the middle, 0.68 to the right, and negative 2.93 to the left. So is that our number line that we're looking at? So this is D, E, F. All right, and now that we've done that, we took the second derivative, set it equal to 0, we solve for x using the zero product rule and the quadratic formula. We can now say that D, E, and F, those are all critical points where the concavity is 0. And what we'd like to know is, what is the concavity in between them? So what is the concavity like over here to the left? What is the concavity like in here? What is the concavity like in here? And what is the concavity like over here to the right? And the good news is, because these are the only these are the only inflection points, the concavity in between two inflection points will always be the same. So if I just choose any random point in there and it turns back concave up, the whole region is concave up. And if I just choose any test value at all from here, and I test it and it's concave down, then the whole region is concave down. And that's what we're guaranteed. So let's try our test values. What value should we try? What's a number to the left of negative 2.93? Yeah, try negative 3. What's a number between 0 and negative 2.9? Negative 1. Try negative 1. What's a number between 0 and 0.68? Yeah, 0.1. Sure, why not? Try 0.1. And a number bigger than 0.68? 1. So those are our 4 test values that we're going to try. And what are we going to plug those numbers into? It says for each of the following intervals, tell whether it's concave up or concave down. So what am I plugging these numbers into? I want it to tell me if it's concave up or concave down. So we plug it into the second derivative. So now I need to find f double prime of negative 3. I need to find f double prime of negative 1, f double prime of 0.1, and f double prime of 1.
So we have 240x squared cube.
Right, we are, and we already have our function here. So I'm going to write that down once. F double prime of x is 240 x cubed plus 540 x squared minus 40x. And I don't think there's too much mental gymnastics we can do to figure this one out. I think we just have to actually plug these numbers into the calculator. So here's a thought, because maybe you don't want to sit there and type this whole function into your calculator more than once, and maybe you don't want to go back and enter it and type in all those different numbers. What we can all do is go into y equals and type in your function like you're going to graph it. So if you just go ahead and go into y equals and type in this function like you're going to graph it, we can all type in 240 x, and then hit graph. Doesn't matter what your graph looks like. It doesn't matter if you have a good window. Doesn't even matter if you can see it. What matters is right now we can hit second trace. And above second trace, you see the word calc. If you hit second calc, the very first option is value. And now you can just plug in these 4 values. So x equals negative 3. Bam, it's just going to tell me that answer was negative 180. So that first concavity was negative 180, which means concave down. My second concavity now, again, I hit second trace, value, negative 1. That was positive 780. Notice these numbers don't matter. The fact that it's 180 or 780 doesn't matter. The fact that it's negative means concave down. The fact that it's positive means concave up. And then plug in 0.1, so again, second trace, value, 0.1. That's negative 42.36. Doesn't matter, it's negative. And then second trace value 1, that's positive 300. So there we go. This whole technique that we just did here is called trying test values from each interval on our number line after we found our inflection points. So then what could I do now? I can look back at my number line and I could just kind of draw a little sketch and say this whole region is concave down, and this whole region is concave up, and this whole region is concave down, and this whole region is concave up.
How do you do the second trace?
Oh yeah, so you would hit second. So now that you have it over there, well, first you have to go to graph. Now that you're in graph, there. Now there's your graph. Now you hit second trace. And the very first option is value. And you just type in any number. That's one of our test values. And it will calculate it for you.
Oh,
Did everyone get their calculator to work?
Okay, that's what's so fun. You've got that x here, that's squared, that's x. Let's go to graph. That's graph. Second value. Oh, it does say value. No, so I think that's because our window is up. Yeah, your window is only going left one, right one. Your window has to at least cover the region that you want to type in. And that's, I'm just changing everything to 10 all the way around. Now you'll be able to do it. Good point. So Sarah found out that if your window isn't big enough to cover the values that you're typing in, it's not going to give you any calculations. That's why did your calculator work? So under y equals, you're going to now type in the whole function, which was our second derivative. So what? 240x cubed plus 540x squared minus 480x. And then your window is already good, so you graph it. There's your graph. It doesn't really look all that good, but now you can hit second trace above it says calc, and you can choose any value to input. And you can input, like, say, 3. And that's what you're about to plug into 3, and it tells you it's negative 1. Give that a shot. Molly, did it work?
No.
Oh, well, let's see it. So you have your graph. Oh, I think it's because your plot is on. Sometimes the plot that's on is going to throw it now it's graph. There you go. Did it work? Oh, yeah, with the y1. Sure. Did it work? It's because if your function is 540 squared.
Oh, okay.
You just need the x. So right there you go.
Oh, okay.
These are mistakes.
That should work. Okay. Sure. Okay. 1. Okay. All right, well, there we go. Now, keep in mind, what we just accomplished is giving some fairly disembodied information. Do we know yet what the graph looks like? And forget the fact that we graphed it. Can we tell from this what the graph looks like? Not really. All I really know is that if I tried to graph this thing, and I put myself a 0 and a 0.68 and a negative 2.9, okay? All I really know is that my graph should be concave down here, and then it has to switch and become concave up, and then it has to switch and become concave down, and then it has to switch and become concave up. And actually, through sheer dumb luck, is that actually what our graph ends up looking like? Pretty much. It kind of does. Remember, let's go back and look again at what the graph looked like. There. Is that what it looked like? It went all the way up, concave down, then it came down, and went to the right, and then down, and then up. And is that what I just drew in blue? Yeah. But, I mean, I was heavily influenced by the fact that I knew what it looked like. So if we really wanted to finish this analysis, we would have to go find the minimum point, the transition point, the x-intercepts, maximum up there. And once we have all those points, this x-intercept, once we have all those points, then we could go about sketching a really nice curve. So all we really accomplished right now is just getting concavity information, right? So all we did was analyze this function from the perspective of concavity. But that's it. That's the end of the problem. So what would they want us to type in? The interval over here to the left was concave down. And this interval between D and E was concave up.
And this interval between E and F was concave down. And then this interval from F to the right is concave up. Questions or thoughts about that one? What did calculus really give us in this problem? Because we could have just graphed it on Desmos, right? So what did we really find that Desmos couldn't tell us? That we didn't actually know where those points were on Desmos. If you just went to Desmos, you would have seen exactly what the graph looked like, but you wouldn't have known the exact changeover points. The one at 0, maybe you could have figured out and seen. But then the other ones, 2.9 and 0.68, that would have only been possible from solving this quadratic formula, which you only knew how to solve that quadratic formula after having taken 2 derivatives from the original function. So that's what we really gained out of all of this calculus know-how, was just where the actual 2 inflection points were. Okay, let's do another one. Oh, right back. So number 14, we have a rational function. Why do we call that a rational function? Why is it called a rational function? Because it's a fraction. Exactly right. Rational should be pronounced rational because it's a ratio, because it's a fraction. All right. And so now what do we want to do? Consider the function. You'll never be able to read that word the same, right? Consider. Consider the function. So for this function, there are 2 important intervals, to the left of A and to the right of A, where the function is not defined at A. Now that's interesting. Notice now what they're saying. Not defined at A. So they're saying it's not defined at A. So there's an asymptote or a hole, or probably an asymptote. But notice that's interesting because so far we have been looking for inflection points, or we've been looking for critical points, or we've been looking for x-intercepts. But this is a new idea, not just an x-intercept, but a asymptote, or where it's not defined. So the first thing we want to do then is find A. Where is that function not defined? Correct, when the denominator equals 0. A function is undefined when the denominator is 0. A function is undefined when you square root a negative, and a function is undefined when you log a 0. Those are all 3 situations where a function is undefined. And so we just need to know when is the denominator equal to 0. So 3x plus 3 equals 0 when? What? X equals -1? Yeah. So now we already know our A value. So find A equals, sorry, -1. Is that right? Yep. So now for each of the following intervals, tell whether f of x is increasing or decreasing. So we're going to make a number line. We're going to put -1 there. And we're going to choose a test value to the left and a test value to the right. So what's the number to the left of -1? And what's the number to the right of -1? 0. Great, we're going to try -2 and 0. And since we want to know if the function is increasing or decreasing, what will we plug these numbers into? We want to know if it's increasing or decreasing, so we'll plug it into the first derivative. So what we want to find then is find f prime of -2, and we want to find f prime of 0. And whatever those are, we're just looking to see if it's positive or negative. Right? So that's one thing we're going to do. We now have to go find the first derivative. So let's do it. The first derivative, how would we find it? F of x is 2x plus 7 over 3x plus 3. What rule will we use? Quotient rule. And that looks like O d high minus I d O all over O. So, is that ready? Set up your work. Okay, ho d high, what's the derivative of the numerator? 2, so just 2. minus high d ho, the derivative of the denominator, is 3. Again, because the derivative of 3x is 3 and the derivative of 3 is 0, so just 3. Okay, so now we just get to clean up that whole numerator. How do we clean up the numerator? Distribute. Let's distribute our 2, distribute our 3. Be very careful with that minus sign. So we have 6x plus 6, and then we have minus 6x minus 21. We do all that right? Ooh, what happens in the numerator? I get so excited anytime you can cancel out a variable. The 6x's cancel out, and we just have 6 minus 21, which is what, negative 15? Well, this is really exciting. This is the first derivative. I absolutely love it when I have a function where the only variable is inside of something being squared. Because what is the value of anything that is squared? Positive. And so we have a negative number divided by a positive number, and a negative divided by positive is negative. The derivative is always negative. Can the derivative be 0?
No.
Could this be 0? If it were, it'd be undefined. So truly, we now have a derivative that's value is always negative. And so now I can already come back to my number line here and say that my derivative of negative 2 is negative, and my derivative at 0 is also negative. And therefore, it is decreasing over here, and it's decreasing over here. So there, that's my first test values. Notice we didn't even have to plug negative 2 and 0 in because we already knew that the first derivative is just always negative. Josh? Well, it could be 0, but then 15 divided by 0 is undefined. So yeah, this thing will never equal 0. It will only ever be a negative number. Yeah, so that means that our function is always decreasing because we only had one critical, no, it wasn't even a critical number. This was an undefined point. This was an asymptote. So to the left, we're always decreasing, and to the right, we're always decreasing. What does that look like? Can you imagine a graph that's always decreasing? We didn't look at the graph yet, did we? What does a graph look like that's always decreasing? With an asymptote. So it's always decreasing. Let's look. 2x plus 7 divided by 3x plus 3. That is a graph that's always decreasing. It's funny, it's different from what you'd expect maybe. So over on the left, we're decreasing, 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 decreasing. Jump up infinitely far. Decreasing, 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 decreasing. Somebody, like a smart aleck, might say, well, you're not always decreasing because right here you do jump up infinitely far and then keep decreasing. But technically, the function itself is always decreasing. This jump is not what the function does. Okay, so we can all sketch a graph of it now. Let's sketch a graph of that so that we can all agree that indeed our graph is always decreasing. Now, to answer the next question, we can cheat and look at the graph. The next question says, note that this function has no inflection points. Is that true? Are there no inflection points? Because over here, it's concave down, but over here, it's concave up. Well, why is there not an inflection point? It changes from down to up. Yeah, but it's not at a particular point. It's an asymptote. So there is no inflection point, right? But we can still consider the concavity. So to the left of the A, what is the concavity? Down. And to the right of A, it's just concave up. Now, we did just massively cheat in answering that second question. You know, I use the word cheat loosely, but we didn't do any computations at all, did we? How would we do the computations? Yeah, we'd have to take the second derivative. And whether you write it down with me or not, I just want you to see that we'd have negative 15 over 3x plus 3 squared.
That's our derivative. Now we have to take the second derivative, which, do we have to do the quotient rule?
No, you can just move it up to the.
Right, I can just push that term up to the top. Very good, thank you, JR. And so now I just have 3x plus 3 to the negative 2. So it's not a quotient rule, it's just a chain rule. Because we do have an inside function. So I'll go ahead and chain that out real quick. So that'd be 30, 3x plus 3 to the negative 3 times 3. And so that would be 90 all over 3x plus 3 cubed. Okay, so that's our second derivative. And we would do a test case, same thing. And in fact, I'll just go ahead and put my test case right below it. So now if I plug in the second derivative at negative 2 and the second derivative at 0, we should be able to do this in our head. So if I plug in negative 2, 3 times negative 2 is negative 6. Negative 6 plus 3 is negative 9. Negative 9 cubed is a negative number. 90 divided by a negative number is negative, and therefore it's negative. Which means it's concave down, which is what we knew. And now if I plug in 0, 3 times 0 is 0, 0 plus 3 is 3, 3 cubed is a positive number, positive divided by positive is positive, and therefore the concavity is positive, which it is. So you can see how I play really fast and loose with my calculations towards the end. Because all we're interested in is whether or not it's positive or negative. The actual value itself doesn't matter. All right. Questions about what we just did? All right.
So, like sometimes I have trouble
Me too.
with the concavity.
Yeah.
It's like, well, with the fact that it's like a min and a max. So the max is below.
Well, this particular graph doesn't have a max or a min.
It's like the one on more. It's like asking it's a max on this. And okay.
Not on this particular function, right?
Yeah.
On this function?
Yeah.
You have to show it.
Yeah, I'll show you.
Okay, you show us. Okay. Yeah, well, let's definitely take a look at it because I want to answer your question. Okay. All right, well, that's it for number 14. Let's try another one. This one says, consider the function, and what does this graph look like? Yeah, we don't know, right? This is a truly strange looking function. I don't know what it looks like. But they're asking us to find what? They're saying for this function, there are two important intervals to the left of A and to the right of A, where A is a critical number. So we're looking for a critical number. What does that mean we're going to do? Set the first derivative equal to 0 and solve for x. So we're going to find our critical number, and then they just want us to tell us if it's increasing or decreasing, concave up or concave down. Okay, this is going to be really nice. We've practiced this whole test interval, test value a few times. This will be another really good practice doing both first and second derivative. All right. And we're not even going to cheat and look at the graph. We'll just go blind on this one. So, we want to find the first derivative. Everybody go ahead and write it down, and let's start taking the first derivative. We can finish this problem before we go. So, function 6, x minus 2 2/3. So to take the derivative, what rule are we using? We have an inside function, so it's definitely the chain rule. And otherwise, it just looks like a power function. The coefficient comes along for the ride. So it's a chain rule with power rule. So we do the outside, derivative of the outside. So 6 times 2/3 times x minus 2 to the 2/3 minus 1, which is really minus 3/3, which is really negative 1/3, times the derivative of the inside. What's the derivative of the inside? It's just 1, because the coefficient on x is a 1. Okay, now let me clean that up. So that's 4 x minus 2 to the negative 1/3. Does everyone agree that that's our derivative? Because the problem is asking us for concavity and, well, yeah, we might as well go ahead and take the second derivative, because later on they're asking us to talk about concavity. So we might as well take the derivative now. So one more chain rule. So second derivative, that'll be 4 times negative 1/3. Leave the inside function alone. What's negative 1/3 minus 1?
Negative third minus 3/3? Negative 4/3? Times the derivative of the inside, but the derivative of the inside is just 1, so times 1, I'm not even going to write it. So now our second derivative is negative 4/3 times x minus 2 to the negative 4/3. All right, we have our first derivative, we have our second derivative. So we just kind of got that worked out of the way. We just did our first and second derivative. So now we still want to find our critical number. So our critical number is when the first derivative is equal to 0. So let's set that first derivative 4 times x minus 2 to the negative third equals 0. How do we solve that? I feel a little confused. What's one thing we could do easily? We want to solve for x, which is wrapped up inside of this thing. What can we get rid of easily? Yeah, let's just divide on that 4. Make ourselves feel good about ourselves for a minute. We did something. Now what? Log stuff?
Turn it into a log.
You know, we don't have to turn it into a log. You only turn it into a log if the exponent has a variable. In fact, logarithm means exponent and variable. I just made that up, but yeah, it does. So we don't have a variable in the exponent, so we don't have to do the log. But we do want to get rid of the negative 1/3. If you wanted to, we could push the x minus 2 down below, and then we could call 1/3 a cube root. Does that help us? Sure, we can cube both sides, and then that way we have 1 over x minus 2. When is 1 over x minus 2 going to equal 0? When is 1 divided by something ever going to equal 0? It's not. This was a little surprising. It took us a second to realize. I mean, if I wanted to right now, I could multiply both sides times x minus 2, and that would, get rid of it, and then I'd have 1 equals 0. Then what this tells us is that this function, the first derivative, is never going to equal 0. It's never going to equal 0. However, could it ever be undefined? Let me go back a step. Could this function ever be undefined? Yeah, if what? When could it be undefined? If x was 2. So let's remember, we haven't talked about it today, but a critical number is whenever the first derivative is equal to 0 or equal to undefined. So there's a possibility we just kind of forgot about. So let's remind ourselves. A critical number is when f prime of x equals 0 or undefined. And going back to the very original function here, if I had written it differently, we might have seen this better. F prime of x is equal to 4 over the cube root of x minus 2. And could this thing ever be undefined? Yeah, if I let x equal 2. Because then 2 minus 2 is 0, the cube root is 0, 0, 4 divided by 0 is undefined. So our critical number is our critical number. X equals 2 is our critical number. Not because it creates a flat spot, but because it's undefined. So how about, I know that we're just about out of time here, but we can at least set up our number line. 2 is our critical number. That's the number they're calling A. So choose a number to the left of 2. To the left of 2. 1. And then a number to the right of 2. 3 sounds great. So we're going to try those, and because the first question says tell whether it's increasing or decreasing, we know we have to plug it into the first derivative, because that'll tell us if it's increasing or decreasing. And then we also want to know for the second question if it's concave up or down, so we have to plug that same numbers into the second derivative. And that'll tell us if it's concave up or concave down. So this right here is kind of the real work that we're doing. This is a number line. Our 2 was our critical number. And we're just wondering what's happening to the left of 2 and to the right of 2. And if you'd like, because I think we have enough time for this, we could just look at the graph real quick and see what they're talking about. This was 6x minus 2 to the power of 2/3. And sure enough, look at what a weird little point 2 is. That wasn't nice of me. 2, you're not that weird. Let's see, I want to go down 10 and up 40. There. What is 2? It's a cusp. So we can now answer all 4 questions. What's happening to the left? Increasing or decreasing? Decreasing. What's happening to the right? Increasing. What's happening to the left? Concave down or up? Down. What's happening to the right? Down. So there, by looking at the graph, we just answered all the questions. But technically what you should do now is actually go plug those test values in and see what you get. And yeah, it would take at least another 5 minutes to finish that. But now we know, in fact, I can go ahead just based on my memory of what this graph looked like. I now know that decreasing, that's going to be negative, that's going to be positive. The concavity is going to be negative, the concavity is going to be negative. There, that's massive cheating. I just put in the signs I know to expect. But you should still go back and plug 1 and 3 into both your first and second derivative. You just type it into your calculator and see what you get, and you should get those pluses and minuses. Okay, well, wonderful, folks. There's only one problem that we didn't do, right? 16? Okay, we can do that next time. Rosa, what was your question?
So it was the derivative of 1
Yeah.
is negative.
That's going to turn out to be negative because it's decreasing. Remember, it's decreasing to the left and increasing to the right. So decreasing to the left, increasing to the right. Yeah. Okay, really nice. Henry, you want to tell me what that more question was?
Yeah, it would probably be on 2.7. Right there. Oh, you're gonna hold it.
Hey, thank you, folks, for your questions, your comments. If you have any questions at all, please come see me right now up in office hours.
And like, we don't need to come see you for the test, but it's, just fun.
Correct, yeah, you don't have to come see me anymore. But yeah, just for fun, you could. Hey, see you now. All right, Henry. Section what?
2.7 probably, right?
Yeah.
I think so. And it'd be, I think it was like 7.
See, Josh. It could be 5 that you're talking about.
Yeah, I think it was.
Yeah, it's 5. And Henry, would you believe that number 5 is the problem that we're about to do? It's the last problem from the section. But did we do a problem like that? I thought we did. Yeah, we did number 5. Yeah, it was number 5 in our previous packet.
Right.
So
I got the answer right, but like at first I put it in the wrong spot.
Well, let's look. So let's see. Here's 8x plus 7 over x. And so, yes, to your point, you were saying that the minimum is above the maximum.
Right. So that's weird.
Yeah, I can see why that's funny. That the minimum is above
That's
the
where it
maximum.
is, right? That's
Yeah.
true.
Yeah, in fact, you want to see a really terrible function?
Or,
No, it's not that one.
I like that function. If you put that on like a piece of art, people would like it.
Yeah, they would. Darn, what is the function I'm trying to do?
Tan, I used to-
Oh, I know.
Numbers.
There. It's easier. Here is an infinite array of minimums above the maximums. Infinitely many of them.
I don't like
It's kind of funny.
it. It's true.
I wonder if it'd be possible to push them down so that,
They're just above and just below.
or even right at the same level. I don't know how to do that. I mean, I could try, I could cheat. There. Oh wait, that was wrong. Oh no, oh yeah, that was wrong. They certainly got closer to each other. Now the min is above the max by only 0.02. So they're awfully close. I don't think we can actually get them to be one below the other. That'd be really cool. How can you create a function? Let's see if we can create it.
Because they would have to be at the same x values.
No, this would be allowed.
On that.
We must be able to do this. I want to do this. How could you create a function that goes like that? And I don't care if it's infinitely many, but infinitely many would be cool. How could we create that function?
So it would kind of be, I mean, you can't just add functions, but it would be a combination of like a negative x to the fourth or something, or more like x to like the eighth. And positive. Like, I guess you're going for that one function we just looked at, where we had the rational function.
Mm-hmm. Yeah, so even here, I think there is a way to make them flip-flop, but I don't know what it is. I'm suddenly really wanting to know how to do it. Oh, okay, there, that one flip-flopped. Oh, I suppose if I just keep, oh, in fact, I get rid of the squared. And then I just keep doing that. But how do you get them to go higher than the other one?
Right. Maybe what if you put some of the, the art things in the parentheses on the top of that polynomial? It just makes it wider.
Oh, you know what, the ones that, oh, actually, the ones in the top are x-intercepts. So let me create an x-intercept. Well, this already has an x-intercept. Wait, no, that's not an x-intercept, that's a maximum. Okay, what if I create an x-intercept at +3? Oh, but then it flipped over to the other side. We don't want that, we want them to continue to be. But what if then each of these needs to be squared? Right, that might be it. No. Okay, well, I don't know. This is a good exercise, though. Like, how would you go about creating it?
Because you can't just say, I mean, you can make a table, but if you took a table, you couldn't just like put a table, like do any arithmetic with a table to find the equation, right?
Yeah, plus you want a function. You want a function that will do that.
You could be like, I want when x is 5 to be like 6, and when it's 6, I want it to be 4.
Right. But I can tell you that this type of question, see, this is a very high order question. I want a function to look like that. But the fact is, we have no experience to even begin guessing. Well, what would that be? Would it be rational? Would it be square roots? Would it be cube roots?
Like mathematician people in general don't have the way they do it.
No, just you and me.
Yeah, no.
You know, it's a very open-ended question, and that's what makes it so exciting. Because you know, it's not like anything you've done before, and therefore,
Leibniz would know.
I mean, probably. I bet there's some sort of simple insight, like a very simple insight, that once we had the insight, we'd be like, oh, well, yeah, you just do this, and then you have a function that does that.
If I bring it Thursday, will you make everyone